how does that look? I think we can all see that, right?
That looks great.
There is the actuator. So what we have is out here at the end, this is what you call the end effector.
Correct.
And the first thing I thought is like, well, wait a minute. In my quaternion drive, I was thinking sticking a motor right out there. So I was wondering, do you actually have the drive unit for this back here ensconced inside of this upper atmosphere, upper hemisphere?
Mm-hmm.
And then, of course, we have this hemisphere here, which rotates basically at a 45-degree angle. So that's kind of the idea, the trick of what's going on here. And this one here actually rotates vertically. So we see that hemisphere going around. Now, I've kind of done it backwards. The first one is the blue.
Yeah.
And the reason why I'm picking blue is that's the Z direction. So we can kind of see that's rotating in the Z direction. And this one right now, the way at least I have it in the neutral position, that's in the X direction. So we can see it going around. And notice we had to put these notches on here so you can actually see it rotating. Otherwise, it's so symmetric, you have no idea. And then normally I would have like a green actuator in the middle for, for Z, Y, X or something like that. But this isn't pointing in the normal principal direction. It's technically in the Z direction because you go Z, rotate 45 degrees, and then you go about the new Z, and then rotate another 45 degrees about the new Z. So technically, it's what you would call a triple roll wrist. In this case, since it's not really any principal axis, I mix blue and red together, and you get magenta. Okay.
Oh, I like
so
that.
It's somewhere in between. So just so we kind of know that. Now with this, there are some restrictions in your movement, which are actually intentional.
Yes.
And there are also some side benefits. So would you like to point out what some of those are?
Sure. So in terms of restrictions, you'll notice that it's stuck at a hemisphere right now. And that's very intentional.
Yep.
One benefit to that is that because it's restricted to that hemisphere, and just as an aside, we can't increase that to more than a hemisphere, but we decided on this very strategically. It's so that there are no collisions when, say, you use this in a system.
Yes.
Additionally, there are no pinch points. Well, I guess there's one pinch point, but you can change the shape of the end effector.
Yep.
So that's something that is really much safer than, say, the Orbita actuator.
Would you like to explain this little hole at the end?
Yes. So one of the things that I wanted to just get out of the way is I wanted a system that let me route wires without the wires impeding the continuous motion of the system. So that hole is a through hole that, when paired with something like a slip ring, would allow wires to go straight to the origin point of that joint, allowing for continuous motion.
Bigger. And now there is an intentional reason. Again, this is one of the things I pointed out. If you might remember, I looked at, this is the typical wrist that you actually see on a shoulder or a hip, where you have a rotation out here, another rotation here. So that's usually what they call the fourth. And then you have your 6th axis right there. Now, depending upon how you build this wrist, and if we could get around so everyone can kind of see what's going on there. So we have this wrist here, which is also able to rotate, or that axis. Now, you could build the actuators in at each joint, and they actually form the joint, which is typical in humanoids, as we'll see. Or you see these motors that are way back here. There's actually a very long transmission system that comes out here, and some really fancy mechanics to get them to work. So you're not actually carrying the load of these actuators out here. So it is possible to create something like that, but you do provide a little bit of complexity. Now, these were the painting robots that we're talking about. And the reason for the painting robots is that these kinds of robots, when you try to put any sort of system on them, and let me see, I think this one here actually kind of shows that. If I go ahead and I want to have some end of arm tooling on here, you see the cabling has to be routed externally. It gets in the way, it gets snagged. And the idea of the paint robots is that these things are horizontal.
Oh, we saw something like that at the International Conference for Robotics and Automation the other day.
Oh, yeah. That was convenient for you, Michael, wasn't it? Because you were right in Atlanta.
Right.
Yeah. I was thinking, girl, it was like a 7-hour drive for me, and I was just at the Automate show the week before. It's like, I should have gone. But
when we saw that thing, I looked at it, and then Bryce, he said, here's what makes us different. He said, that's a cone in the socket. He said, we have a ball in the socket. I said, that's all you need to tell me.
Yep. So I guess you could say there's similarities in that you've got three actuators that are kind of stacked inside of here, as well as they have over here. So your motors are basically in the base. There's absolutely nothing up here in actuation. This is using a kind of parallel actuation strategy, which is really interesting. And that it's, if some people are familiar with the Stewart platform, it's like almost kind of like that, but it's definitely, it's a parallel kinematic. And what I'm going to do is I'm going to show that, if you move all of them at the same time, then you can see you can get pure roll out there at the end. If you decide to take like just one of them and move them, let me see if I get that there. So, or let's say the other two. So you see I have the blue and the green rotating there, so that it's kind of fixed on the X. You're able to get kind of a tilt that way. And then you can do a similar thing here the other way. Now you're going to be very careful, because you very quickly can run into trouble that they're going to bump into each other. So you don't have an infinite range of motion. So it's far less than a hemisphere of what you have here. And so the applications you would have for it are a bit more limited. And we do see, it's like, well, yeah, there's some pinch points in there you have to worry about, but still it's a clever design. It's one of these things that, I also was intrigued looking at it and thinking of like, where is the best application for it? Now, this is something Paul and Robotics came up with, I think, quite a few years ago. They wrote a paper on it already back in 2020, and they only use it in their neck.
Well, they use it in the wrists now too.
Oh, they are using it in the wrist. Okay,
Yeah.
so at first I did not see it in the wrist. So what we can do is we can kind of look at like, what's the practicality of this? So the first thing you could say, all right, if you put this at a head joint, what would be the utility of it? And again, see, with our heads, we have kind of a limited range of motion on the head. In that, you might want to say that the one thing the head can do is you can kind of tilt back and forth, right, from side to side. And so that's one thing you can do. And you'd have to line this up right, because the range of motion it has this way is plus or minus 35 degrees. So you really can't go down like that if you want, without the whole thing tying itself up in knots. And as you can see, these actuators go through each other. So you're limited that way. So you have to choose the direction you want correctly. And then there is the, okay, so that's the knotting. And then I think I have this one forward and backwards. This is a rather interesting one, is it can go plus 60 this way and minus 30 that way. So you have like 90 degrees of travel, but it's non-symmetric. And maybe when you're looking down, yeah, we tend to move our heads down more than we do back. Some of you might be more flexible, but when I try to go straight up, I got to use my eyes to look straight up. I can't do it all with my neck. So you might say, okay, that's a reasonable range of motion for that, but it may not be reasonable for a shoulder. It's definitely too limited for a shoulder. And in the wrist, I also said, okay, let's see what it's like with the hand. So it's going to be the same thing, is that you have to select it carefully with the hand. That if we look at our palm and we try to do what would be a pitching motion, we do tend to have more movement coming down than we do going back, but it's definitely more than a 360. So let's see, I think, okay, so side to side, our yawing, we don't have much. So like plus or minus 35 is almost acceptable for the yaw, but unless they did something a little bit different with the design overall, you're like, oh, okay, I can kind of get what maybe a very arthritic human would be able to do with the wrist, but not get fully down. Yeah, go ahead.
Are you sure it's not symmetric? I think the red would have to move as well for it to go back farther.
Well, yeah, see what you do, it sort of depends if you're looking at yaw and pitch. So this is weird, because these are 120 degrees apart. And usually when we think of yaw and pitch, we are lining them in a particular way. So what I'm doing is I'm saying, looking at this cross axis here, if you want to get that movement that way, the red axis stays fixed and the other two move.
Oh, yeah.
And because of that, their range of motion is interesting. See, forward, they can kind of come back. So you see these little actuators that come back and they bump into each other. And when they come back, they have more, because only one of them is moving towards the red, relative to the red. It can move the full 120 in that direction. But when you go this way, which you need to do to go forward, you see what ends up happening is they're both moving towards each other. So even though they start out with 120 degree separation, the closing distance closes, you get 60 degrees of travel. And so it really depends upon where you decide to align your hand out. So you have to be very careful. You just can't stick the hand on there anywhere. And that's why I picked along here, is because this is the restricted movement, or let's say this is the movement where I wanted to get 90 degrees of movement. So this allows me to get 90 degrees of movement. Whereas when I go this way, I end up bumping in because basically all three are needed. And so what happens is they're all kind of racing towards each other one way or the other. And so I'm going to end up bumping in one way or the other. And that's why I have it like, yeah, plus or minus 35. And then the other thing, of course, you can do is you can take it and then spin it around like this. And I imagine you could probably spin it almost a limited amount. But it's a little bit different. I'm not sure about cable routing, whether they're able to route through the center or not. You're already able to do that. We do have these pinch points, and the other thing is getting sort of like IP certification, where intrusion protection, and what level that would be. That you have to make sure your joints are well sealed, so you don't get dust and water and everything. Plus the other thing is that you would have to put something around this thing to cover it all up, because these are moving joints that could be hitting things. So you would like to have it in some sort of cover, which I imagine, be a flexible covering that you would have to do that. And we can see the way they're doing it right here is that they have 3 motors down here, and I'm not sure what the torque profiles are like on those things. So that might be enough for moving ahead.
If I remember correctly, I think each of those motors outputs 1 Newton meter of torque, and then there's a planetary gearbox that coincides with each motor, and those stack on top of each other inside of that cylinder. And the outer ring of those planetary gearboxes are what rotates each of those linkages.
Okay. Oh, yeah, exactly. So you do have them sort of inside there. And this model, which is an open source model that you can get, sort of shows the gearing, and that they have like that inner ring, and then they have the other kind of pinions that go on there to rotate it around. And that's another thing I wanted to kind of point out about your design and what you're doing. And I'll just kind of briefly stop sharing so we get more back into a discussion here. So we can see this green joint, the way it goes back, and oh gosh, look at ouch, look at that. Okay, so we can see kind of the problems that you have with that kind of joint configuration is it just wants to go into itself. All right, so and we have the same thing here down the hip, and then over here on the left side is where we have the orbital actuator on here. And we can see if I try to move the purple joint, no matter how much I move it, it just will not allow that forearm to come into contact at all. It won't. So I can move it around that way. And then I have a standard actual flexure right here for being able to move around in the flexion. Okay, now what I would like to do is show this. I'm using some really rough Jacobian inverse kinematics to allow me to move this thing around. So we can sort of see what happens when we try to move the end effector. Now, of course, I can drive the upper arm through the torso. We can do that ourselves, okay? But our ball and socket joint does make it kind of difficult to drive our upper arm into ourselves. We can a little bit, but it's sort of restricted because that's the nature of a ball and socket joint. But as you see, as I come around here kinematically, it just won't allow that to intersect. It's just, it's like, sorry, no way, you cannot do that. And so that's one of the things that's really interesting about this wrist. And at first, I wasn't sure how it was going to behave when I started to give it some inverse kinematics. And I actually have been quite impressed with how it works.